Welcome back everyone. So today I picked up a problem from Parabola under coordinate geometry section of mathematics, but interestingly we'll solve this problem using some concepts of physics, right? I will use the projectile motion analogy. I'll explain in the video. The main reason behind picking up this problem was just to trigger your out of the box thinking skills, right? If you solve this problem in conventional manner, you might get a very lengthy solution, but my approach will give you a very quick solution. I mean, if you can crack this in the exam time or in the meantime. So let's read out the problem once. P, Q, R and S are 4 points on tangent at P to y square equals to 4ax. It is definitely a parabola such that PQ is to QR is to RS is 2 is to 5 is to 7. Perpendiculars from QR and S on double ordinate of P cuts parabola at M, N and K respectively, where Q, R, S are on the same side of P on tangents at P. If Rn equals to 3, then Sk upon Qm is equals to what? So let me draw a rough diagram first. This one is, let's say, y square equals to 4ax parabola. And let's say this is point P and we have drawn a tangent at P, and Q, R, S are on the same side of P on the tangent, and this one is the double ordinate of P, double ordinate of the parabola corresponding to point P. So we'll draw perpendiculars from Q, R and S on this double ordinate, and this will be M, N and K as mentioned in the question. So we are supposed to find Sk upon Qm, these two ratios. Okay, but interestingly I will not use the parabola y square equals to 4x, and I'll still claim that the result will be the same, because you can see that in answer there is that a is not mentioned, still you will get a definite value of Sk upon Qm. So it is basically independent of the parabola, what parabola we are talking about. It is basically kind of generalized property. So we can prove it in generalized way, but I'm not going to prove that in my video because I'll show you some other technique that will be a bit interesting, I guess, using the projectile motion analogy. Let me move on to the solution. So the parabola what I am talking about is the trajectory of a projectile motion. Let's whose initial point of projection is P. Yes, I am assuming this, but this will give the same result what are asked in question. And I have projected with a velocity u at some angle. So this will be the trajectory, let's say, kind of a parabola. Or let me draw a bit better. Let's say this is u and this is the parabolic trajectory. So from kinematics I've already studied that S equals to ut plus half gt square, and now I'll use its vector form. So if we vectorially add these two terms, that is ut plus half gt square, we will get S vector. S is the displacement vector and ut is a vector in the direction of initial velocity, whose magnitude is u times t, and half gt square is definitely vertically downward as g is vertically downward. So at some point, let's say after t time is elapsed, the particle is somewhere here. So this will be the S vector, and this one will be ut vector in the direction of u, and this will be half gt square vertically downward. I have added ut plus half gt square using triangle law and I've got S vector. And definitely P is the initial velocity. If the tangent at P is in the direction of initial velocity, so this line is the tangent ut line. Ut direction of ut vector is tangent at the parabola of the parabola at point P. And on this tangent I have assumed this point as Q, and definitely this one is the double ordinate corresponding to point P of the parabola. So as mentioned in the question, I will drop a perpendicular from Q on this double ordinate, and this will intersect the parabola at this point named M. It is also mentioned in the question. So I am done with PQM in my parabola, which is convenient to my solution. So now I can easily tell that PQ length is equals to UT. Now I am writing only the magnitude, that's why I have not put the vector sign. And QM length is equals to half GT square. So PQ square upon QM will be U square T square upon half GT square, which will give you the result 2U square upon G. And interesting, this is a constant value, and this is true for any point taken on this tangent. I mean, let's say Q is a variable point, P is fixed one. So if we take Q somewhere here or somewhere here or maybe here and drop a perpendicular on the double ordinate and get the point which cuts the parabola, then also PQ square upon QM will be same. So that's the major conclusion, right? That PQ square upon QM is the constant. And now you're all done with the question. So as Q, R and S are on the same side of the parabola, so I can assume R somewhere here and S somewhere here, and in the same method I can prove that PR square upon Rn is constant and PS square upon Sk is constant. So let's say this one is N and this one is K. So I'm writing this conclusion like this, that PQ square is to PR square is to PS square is equals to QM is to Rn is to Sk, and we are given the value that PQ is to QR is to RS is 2 is to 5 is to 7, right? So we can easily write that PQ is to PR is to RS as 2 is to 2 plus 5. Sorry, this will not be RS, this will be PS. It will be 2 plus 5 plus 7. It is 2 is to 7 is to 14. So next I'll use this relation and we'll get the desired result. We are supposed to find Sk upon Qm, right? So Sk upon Qm is nothing but PS square upon PQ square. So Sk upon Qm is PS upon PQ square, that is equals to 14 upon 2 whole square, which is 49. And this is the answer for our question. So that was the idea, that without using the conventional approach, how we can solve this problem in a bit quick manner. So yeah, that's all for today, and we'll come up with some other problems in next videos. Thank you.